Good morning, students. Welcome to the next topic on the second chapter of Standard 12th Physics. Today, we shall be discussing some basic properties pertaining to the electrostatics condition of conductors. Before discussing this topic, conductors and insulators, students, you should know what is the basic difference. So these conductors, they have large number of free electrons. Now what is the meaning of free electron? For example, suppose there is a conductor, say sodium. You know its atomic number is 11. Its electronic configuration is 2, 8 and then 1. So this last electron can easily be lost by sodium so that it attains stable electronic configuration. So out of these 11, these 10 electrons are tightly bound to the nucleus. But the last one electron can easily be lost even by accepting a small amount of energy. Sodium is willingly ready to give this electron. This last valence electron may therefore be considered as free electron. Now what is the meaning of free electron? It does not mean that the electron is completely free to move anywhere. It simply means within the bulk of the metal, the electron can move here and there, but it is not as free that it can leave the surface of the metal. That is not possible. That is possible only if sufficient energy is supplied to the metal. So anyway, compared to the bound electrons, the free electrons can easily move from one place to other within the surface of metal. Insulators, on the other hand, do not have free electrons. They do have electrons, but they are tightly bound to the nucleus. So on applying a small electric field, these electrons, in case of insulators, will not be affected much. They may shift a bit, but they will not move from one end of the insulator to the other end of insulator. With this concept in mind, the first property that I would like to discuss is that in a static situation, the electric field is zero inside a conductor. Very important point. Any conductor, if you take in a static situation, first we have to understand the meaning of static situation. Static situation means that condition when there is no current in the conductor. What is the meaning of current? Current is nothing but the flow of charges. That means the charges are not flowing from one end to the other. Under that condition, electric field inside the conductor is always zero, even if there are external fields or the conductor is charged. Even if the conductor is charged or there are external electric field, the electric field, net electric field inside the conductor must be how much? Zero. So this is first property that you should remember. Now let me try to elaborate this particular property. Suppose we have a conducting material like so. This is a conductor and there is some electric field applied externally like so. So this conductor is placed in external electric field. That electric field I am writing as E. So E is the external electric field. So these electric field lines are actually representing uniform, but it may not be uniform field also. Now this electric field will apply forces on all the electrons, free as well as bound. But the bound electrons are tightly held in their positions by the nucleus. So what about the free electrons? Imagine a free electron over here. electron is positively or negatively charged? It is negative. So it will experience a force due to electric field in which direction? Opposite to the direction of electric field. So it will experience a force in this direction. And what will happen to the electron because of that force? Because of that force, this electron will move from this end to this end of the conductor. The same is true for other free electrons. So the free electrons will leave this end and they will accumulate at this end. Because there is accumulation of free electrons here, so this end will develop what kind of charge? Negative charge. And this end will develop what kind of charge? Positive charge. Now we know the direction of electric field is from the positive potential to the negative potential. So this positively charged end and this negatively charged end will create an electric field in this direction. This electric field which is created due to shifting of charges is opposite to the direction of external electric field. This electric field I will write as E dash. Now what is E? E is external electric field. And what is E dash? E dash is the field due to positive and negative ends of the conductor developed due to shifting of free electrons opposite to direction of external electric field. So the field E dash and the field E in conductors cancel each other. They will cancel each other. Because there are large number of free electrons, this movement of free electrons goes on till this field E dash becomes exactly equal in magnitude to the external field E. If this field E dash becomes equal to E, the net electric field will be this minus this, that will become how much? 0. And that is the reason for this particular explanation. Remember, in insulators also there is partial cancellation. So in insulators, this we will discuss afterwards actually, due to some reason that we call as polarization, there is some electric field developed which is opposite to the direction of external electric field, but they are not equal in magnitude. Due to polarization, the field which is developed in case of insulators, that field E dash is less than E, and therefore the net electric field in case of insulators is not 0, but it is some it has some particular value. So E dash net in insulators, the E dash net is not equal to 0. E net is not equal to 0. Is this clear, students? So remember this fact, inside the conductors, even if externally you apply some electric field, the net electric field inside the conductor will always be 0, provided we are discussing about which situation? Static situation. That means there should not be any current in the conductor. If there is some current in the conductor, there will be electric field inside the conductor. We are not discussing that. Our topic is electrostatics. That means the charges we are considering to be at rest. Okay. Let's see the second property. The second property is written over here. It says at the surface of a charged conductor, in a static situation, electric field emanates normally to the surface of conductor. If there be any conductor like so, and it is charged, suppose it is charged non-uniformly, suppose at this end it has a positive charge and at this end it has negative charge, suppose. Then this statement says the electric field at the surface of a charged conductor in a static situation, of course. That means these charges are at rest, they are not flowing. Now these electric field lines will emanate normal, that is perpendicular to the surface like so will be away from the surface if the end is positively charged and towards the surface if they are negatively charged, like this. Always these electric field lines will make an angle of 90 degree to the surface. That is the meaning of this statement. Let us try to understand why does this happen. See, if possible, let electric field be not normal. We will prove it by contradiction. To the surface of conductor, the electric field, we assume it is not normal. If it is not normal, it will be at some angle. So suppose this is the direction of normal. Suppose electric field is like this. Then we can resolve it into two components, one along the normal and one tangential to the normal, tangential to the surface. This is the conductor, suppose. So one component will be E cos theta along the normal and other component will be E sin theta tangential to the surface. This is conductor. If possible, let E vector be not normal to the surface of conductor, then it has two components. E cos theta component is normal to the surface and there is a component E sin theta that is tangential to the surface. Here you must mention what is theta. I am not writing that. Theta is the angle made by the electric field vector with the normal. If this is so, then due to this tangential component, that is E sin theta, what will happen to the charges? This conductor is charged. So due to this tangential component E sin theta, the charges would experience a force and will move, experience a force and move along the surface. And if the charges move along the surface, will this situation be static? No, it becomes a dynamic situation. So no longer this situation remains static, and therefore our assumption is not correct. What was our assumption? We have assumed that if possible, let E vector be not normal to the surface. If it is wrong, what should be the correct statement? E vector must be normal to the surface. So there cannot be any component of electric field along the surface. The same statement can also be stated in this fashion, that surface of a conductor must be equipotential, because you know students, any equipotential surface, the electric field will be emanating normal to equipotential surface, and for conductors also electric field emanates normal to the surface of conductor. Therefore the surface of conductor is also an equipotential surface, equipotential. So this is about the second property. Let's see some other properties for electrostatics of conductor. The next property is also very important. It says the interior of a conductor, that means inside the conductor, it cannot have any excess charge. Suppose this be a conductor. So this is the conductor. It may be neutral, it may be uncharged. It may be charged. Even if it is neutral, suppose we inject some charge to this particular conductor. If we supply some charge by the method of conduction, suppose, then those charges will not go inside the conductor, but they will reside only on its outer surface like this, and it will not stay at a particular place, rather it will distribute it throughout the surface of the conductor. That means charges will reside only on the outer surface of the conductor. Inside there will not be any net charge. Q net is equal to 0. If net charge is 0, we can say rho. What is rho? Do you remember? It is charge per unit volume. Volume density of charge will also be equal to 0. So this is the statement number 3. Let us now try to understand why is this true. This can be explained on the basis of the first property that we had discussed. What was first property? First property was that inside a conductor the electric field is always how much? 0. Anywhere inside the conductor electric field is 0. Remember this property. Using this we will prove this statement. So we will invoke Gauss law. We will choose some Gaussian surface, arbitrary Gaussian surface GS inside the conductor. Then the total flux through this Gaussian surface will be how much? Total flux will be integral E vector dot ds vector. Now since E is equal to 0 inside the conductor, the total flux through this Gaussian surface which lies completely inside the conductor, it must be equal to how much? 0. But Gauss law says this flux, total flux must be equal to how much? 1 by epsilon naught times Q in. Therefore 1 by epsilon naught times Q in, which is our flux, that is integral E dot ds, must be equal to how much? 0. And that gives you the value of Q in to be how much? 0. So our Q in also becomes 0. Now here this Gaussian surface which we have considered is arbitrary. I can choose this Gaussian surface to be very big, or I can choose it to be over a very small volume. That's why howsoever small volume you might choose, Q in must be equal to 0. What is Q in? Q in is the charge inside this Gaussian surface. So if Q in is equal to 0 inside this Gaussian surface, likewise you can choose the volume element anywhere inside this particular conductor. Therefore this proves that there cannot be any charge inside the bulk of a conductor. If at all you are injecting some charge, where will that charge go? That charge will go onto the outer surface of the conductor. So let me recapitulate again. First property what we discussed, inside the conductor E is 0. Second property what we discussed, that electric field must emanate normally to the surface of a conductor. And third one, inside the conductor there cannot be any excess charge. See, it's wrong to say there is no charge. Protons are there, electrons are there, those things are there, but there is no net charge within a small volume of the element. That we can say by citing that rho is equal to 0. Volume density of charge is 0. Let's see next property. The next property is number 4th one, that is the electrostatic potential is constant throughout the volume of the conductor and has the same value as inside on its surface. It has same value on its surface as its value is present inside. Suppose this be a conductor. So this is any conductor. Of course the situation is a static situation. That means there is no current and it may be charged also. We have to prove that inside the conductor the potential is how much? Constant, and it has same value as its value on the surface. So this potential on the surface and for all points inside the conductor has the same value. Just outside the surface potential will change from V to some other value, say V dash. Now how do we prove that? It's very simple. Again we will prove it using our first property for the electrostatics of conductor. What did it state? It stated that the electric field inside the conductor is how much? 0, property number 1. And second property, that electric field on the surface of the conductor is always normal to the surface of the conductor. That means there is no tangential component. Tangential component if I write as ET, ET will be how much? 0. Using these properties we shall prove this result. See, we know dV, the potential difference, is given by the formula negative E vector dot dr vector. Any 2 points, the potential difference will be integration of this. Delta V is equal to integration dV is equal to minus integration E dot dr from one point to the other point. This must be 0. Why? Because electric field is 0. If dV is equal to 0, The differential V is equal to 0, that means change in V is equal to 0. If change is 0, that means it is not changing, and if it is not changing, we'll write V is how much? V is constant. The same argument you will have for the surface of the conductor. On the surface of a conductor, Et is equal to 0. So therefore there is no difference in potential between 2 points on the surface of the conductor, and therefore electrostatic potential is same at any point inside the conductor or on the surface of the conductor. That's why the entire conductor in static situation is equipotential. Is this clear, students? It must be equipotential. Okay, let's see the next property. The next property deals with the expression for electric field just outside the surface of a conductor, charged conductor. It says the electric field at the surface of a charged conductor is given by this particular formula, sigma by epsilon naught, and in vector notation we use n cap, where n cap is unit vector normal to the surface of the conductor. We have already talked about direction. Let us see how to calculate this particular value. Suppose this be a conductor, and the entire surface of the conductor, of course I have taken in the shape of cuboid, it's not necessary, it can be any irregular shape, does not matter at all. It has plus sigma as the surface charge density. We wish to find what is the electric field at some point just outside the surface, at some point, say here. This point is close to the conductor. So what we do, we choose a small area element like so, and we complete the Gaussian surface in the form of cylinder, and it extends as much outside the surface as it is inside the surface. So this part is inside and this part is outside. So this is our Gaussian surface. Now we will use the Gauss law. Before using Gauss law, we have to find the net flux. The electric field we know, we have already discussed earlier, it is normal to the surface. So electric field must be in this direction. Let it have some value E vector. And suppose this area of the front face of the cylinder has a value A, then this area is also A, and this line shows the intersection of this Gaussian surface with this front face of the conductor. So remember that one face of the Gaussian surface is outside the conductor. It is at that point where we wish to find the electric field, and its other face is inside the conductor, where you know electric field is how much? 0. Now this Gaussian surface, I can divide it into 3 parts. So this is part 1, this curved surface is part 2, and this circular base, other circular base, I'll call it as part 3. The total flux I'll divide into 3 parts, phi 1, phi 2 and phi 3. Phi 1 will be E vector dot ds vector in that direction. So delta S vector or ds vector integral is having a value A and is directed along the outward normal. So the E vector and area vector for this face are in same direction. That's why this will become E times A times cos 0 degree. This is the value of phi 1. For phi 2, you see, if you choose any area element, the ds vector will be normal to the surface, like so or like so or like so, and that ds vector will be perpendicular to E vector, so it becomes E times area element times cos 90 degree. And phi 3 will be 0. Why phi 3 will be 0? Because on this surface electric field itself is 0. So cos 90 also becomes how much? 0. So what is left behind is E times A. So this is the total flux through our Gaussian surface. According to Gauss law, this flux phi must be equal to 1 by epsilon naught times Q in. This is equal to 1 by epsilon naught times. Now what is Q in? Q in will be the charge enclosed within the Gaussian surface. This Gaussian surface meets the conducting surface at this region. This region is also circular and has area how much? A. Now sigma is the surface charge density, that is charge per unit area. If it is charge per unit area and this area is how much? Capital A. Area A will enclose how much charge? That will enclose a charge equal to sigma times A. So that is our Q in. So put this value. From 1 and 2 we will get the expression from 1 and 2. E times A must be equal to 1 by epsilon naught times sigma times A. So A will cancel and therefore our electric field will be how much? Sigma upon epsilon naught. And we have already discussed, students, that the direction of this electric field is where? Along the outward normal. So if you wish to write in vector form, it should be like so, where n cap is unit vector along normal to the conductor, normal to the surface of the conductor. So this is the complete proof for the electric field at the surface of a charged conductor. Any conductor of any shape, it has plus sigma. If it has plus sigma as the surface charge density, its electric field will be directed away from its surface along the normal, having this much value. If it has negative charge density, the only difference will be that the electric field will be towards the surface. So these are the 5 important properties. Based on these properties, one more property we will discuss, that is electrostatic shielding. So irrespective of the value of electric field outside, irrespective of the charges present on the surface of the conductor, inside the cavity electric field is always 0 provided there is no charge inside the cavity. We shall not prove this particular result, but it has wide applications. For example, it can be used to prevent sensitive instruments from external electrical influences. Such sensitive instruments can be put inside a cavity of a conductor. Then outside, even if there are some electrical fluctuations, potential fluctuations, that will not affect those sensitive electrical appliances. And it is for this reason of electrostatic shielding that you are advised to sit inside a car during lightning. So lightning, that if lightning occurs, it creates large amount of electric field in regions outside. So because your car is a conductor, it's better to sit inside the car. So if this is the car, you are inside the car, so that inside portion of the car acts like a cavity. The car is metallic, so don't try to come out of the car, rather you are more safe inside the car because of this particular reason of electrostatic shielding. So I'll stop here, students. Make your notes on this particular topic of electrostatics of conductors. All these points are very, very important, and I will stop here by discussing one simple question based on these particular concepts. So we have a question over here. There is a hollow spherical shell, hollow sphere you can say, that is conducting, and it has some charge. Suppose the charge on this sphere be plus q. Its radius is capital R. 3 points are taken, A, B and C, which lie inside, on the surface and outside the surface. At these 3 points we have to find electric field and potential. See, we have first we shall discuss about electric field. Because this is conducting sphere, electric field for points inside this will be taken as 0. So E will be 0 at A for points inside, and for points outside, if you remember, students, I have discussed the entire charge can be supposed to be present at its center. So at A, this is the answer. At C, the electric field will be how much? 1 by 4 pi epsilon naught. The charge will assume to be present at O, so Q upon that distance square, that is R square. At B, actually we should just outside B, outside the surface, not exactly at B, just outside the surface, the electric field will be how much? 1 by 4 pi epsilon naught q by almost that distance will be equal to radius of the sphere, that is r square. Remember, just at the location of the charge we don't define electric field. We define electric field at points just leaving that particular charge. At the location of the charge, the electric field will shoot up. Knowing these electric fields, we can calculate the potential. Potential, how will we calculate? So potential at any point is given as minus integration E dot dr. This is the working formula, but this we have done earlier. We'll use the concept of electrostatics of conductors. So these are for E. Now let's solve it out for V. First, at C there is no doubt. Potential is as if the entire charge will be present at the center. So 1 by 4 pi epsilon naught q upon that distance, that is small r. So this is Vc, potential at C. And potential at B also there is no doubt, that will be 1 by 4 pi epsilon naught times q upon that distance, that is capital R. Point B is at a distance capital R from the center. What about point A? Do you think it will be 1 by 4 pi epsilon naught q by small r naught? That I am afraid is not the correct answer. Just in the properties of electrostatics of conductors, we discussed inside a conductor all the points we find E is equal to 0. Since E is equal to 0, I have discussed dV is equal to 0, and since dV is equal to 0, V is equal to constant. So we have discussed that potential at all the points inside a conducting surface or inside the cavity will be constant and will have same value as on the surface. So potential at this particular point A will be same as the potential at this point or this point or this point or this point or a point on the surface. So potential at A will be how much? 1 upon 4 pi epsilon naught times q upon capital R. This is very, very important, students. So never get confused. The electric field and potentials at points inside and outside are given by these particular relations for a charged conducting sphere. Okay, students, please practice them properly, and if you have some queries, you can put them in the given link in your website. I thank you. Read well. See you in the next class.